Hi everyone, welcome to my talk, Hindsight Bias, a machine learning story. My name is Mayukh. I'm a Director of Product Management at Salesforce Einstein, based in San Francisco, California. And there I work on our automated machine learning initiative. And I'm really excited to be here in Brazil. So a big thank you to all of you for coming to attend my talk. And also a big thanks to the organizers of PAPIs.io, Louis and Ruben, for giving me this opportunity. Muito obrigado. So, first things first, one of the big things that I want to talk about here is share our experiences building large-scale, real-world machine learning applications. And one of the larger challenges that we face there around bias in data and how we went about addressing that challenge. So if you remember Louis' talk from earlier, he showed a bar graph of the top drawbacks or the bottlenecks people face in machine learning. And right at the top was dirty data. And the second was not enough data scientists to do machine learning. Actually, my talk covers both of them to some extent. So I'm really excited about that. So let's get a show of hands. How many of you know what Salesforce does? All right, pretty good. How many of you know what Salesforce Einstein is all about? Okay. So just to be on the same page, Salesforce is an enterprise customer relationship management company, a CRM company, and we build CRM software in the domain of sales, marketing, e-commerce, services, IoT, analytics, and so on and so forth. Now, Einstein is our artificial intelligence initiative. In each of these areas, there are a lot of opportunities because there are a lot of data, and also there's a lot of manual and repetitive processes. So it's a great place for machine learning to come and augment the life of our customers to make their life easier and make them more productive. In a nutshell, Einstein is AI for CRM. All right. So there's a very popular belief that consumer machine learning is exactly same as enterprise machine learning. I'm here to tell you that is not true. In fact, they are apples and oranges. There are many ways you can slice and dice this difference. One important dimension which is important and relevant to this talk is data. Consumer machine learning deals with known data, whereas enterprise machine learning deals with unknown data. What do I mean by that? Imagine Facebook. We all know it's a consumer company. The data that's inserted into Facebook and made available to the data scientists to build the machine learning models are mostly UGC or user-generated content. This data is gathered to very well-defined user interfaces, methodically designed, whether it's web or mobile. Here's an example of how do you create a status message. You can say that it's a text, or you can say it's a link, you can say it's a photo, it's a video, well-defined interface. You know the schema of the data, you know the metadata, you know when it was created, all very crucial information to build machine learning models. Here's another example. You can react to someone else's status. Again, there is very well-defined 6 emoticons you can choose from. You can't just choose anything that you like. Yet another example, you can comment on someone's status. Again, it can be a text, or you can choose any of those icons for sending emoticons or photo or a video. When it comes to enterprise machine learning, there is a wide, diverse ways of entering data into the system. For instance, this is an example of a sales lead page. So as a salesperson, I can manually come in and enter data into the system. That's just one way. We also have what we call workflow processes or workflow execution or business processes. And they would trigger the generation of data automatically in your system, as in this example. And the last but not the least, everyone is aware of enterprise really survives through integration with other third-party data. So we have to have a way to import external data into our system. And once you do that, you have no idea what the schema is about. You don't know when the data was created. You don't know what the timestamp was. You don't know when the records were updated. And these are very important things that machine learning models need to be aware of, and you need to know these things to do proper feature engineering. That is what I mean by unknown data. And this introduces a lot of nuances and noise in the data. Let's take a few examples. Example 1 is of hindsight bias, also known as machine learning literature as data leakage or label leakage. In this slide, I have 2 identical screenshots of a sales lead. On the left, the lead was created before conversion, and on the right, the lead right at the time of conversion. And each of these fields on the lead, such as the name of the lead, the source of the lead, the number of people in the company, they are features which are inputted as a part of the training data into the machine learning model. And the hope is some of these features have predictive power, and it can predict what is the likelihood of a lead to convert into a sale or a purchase. So it's a binary classification problem. So if you eyeball it, if you observe it, it's almost identical, except there's one little feature there called deal value, which is always populated when the deal is converted. So this feature is leaking information about the target or the response into your training data. So if you use this to build your machine learning model, it would perform amazingly well, unrealistic well in your research environment, but in real world data, that field is not going to be populated, so it's going to perform very poorly. So I'm from Salesforce Einstein, right? So it's apt that I should use an Einstein quote. And Albert Einstein said that if I had an hour to solve a problem, I would spend around 55 minutes to understand what the problem is about and 5 minutes thinking about the solution. So I would like to demystify what hindsight bias is with a very well-known example of Titanic, which entire machine learning community is very aware of. Just to state the obvious, we're trying to predict if the passengers in the famous Titanic ship is gonna survive the shipwreck. And the idea here again is the features of the passengers, such as gender, age, their cabin class, has some pattern into it, which is predictive of whether they will survive or not. So here's some patterns that we see clearly, that women are more likely to survive the crash by just exploring the data. Adults are more likely to die. And here is another pattern that we see in the data set, that passengers who are in the higher cabin class, like B and C, are more likely to survive because they are expensive tickets. They will probably get more privileged access to lifeboats when the shipwreck happened. So I can start summarizing what the machine learning model is going to do. That is, adult men who were at the lower cabin class are more likely to die, whereas young females who were at the higher cabin class are more likely to survive. And so this was used in a Kaggle challenge. It's very famous. Everyone knows about it. What many people do not know about it is that the data that was used in the Kaggle challenge was a cleaned up, dressed up version. The original data had noise and nuances which was filtered out for this challenge. And particularly problematic are two features, boat and body. So if you made it to a lifeboat out of the ship, you were assigned a boat number. And if you died and your body was recovered, you were assigned a body number. Of course, if you have a boat number, you survived. If you have a body number, you died. You don't need a fancy machine learning algorithm to do the analysis for you. To simplify it further, how many of you have heard about or watched the movie Back to the Future? Excellent. So, in layman terms, it's like Marty McFly going back to the future, getting his hands on the sports almanac, and using it to bet on the games of the present. Well, since time travel is still not possible, this is a real problem and we need to solve it. So the deal value that you saw on the sales lead is exactly a feature like boat and body. It's leaking information about the label into your training data. So we need to eliminate those features, else your machine learning model is not going to perform that well in the actual production environment. Example 2, field usage changes over time. So let's analyze what's happening here. So on the x-axis, I have features, which are a part of the training data. And on the y-axis, we have fill rates. That is the percentage of the time the feature was filled in. That is the percentage of time the feature is not null. And on the left, I have the distribution of those features for the training data. And the right, I have the distribution of the data for the scoring data, the actual data it's scored on. For those of us who are familiar with machine learning, we all know that there's a very important fundamental assumption of machine learning. The data that you train on is representative of the data that would be used to score on. And if that is not true, then machine learning doesn't work. Here, there are two features, mobile and referrer, which have statistically different fill rates in the training data versus the scoring data. So again, this model is going to give you great results when you use it in the four walls of your lab, but when you actually go into production, it's not going to perform that well. Example 3, bulk usage by business workflow. So what's happening here? So on the x-axis, we have a time-based feature called last modified date. And on the y-axis, we have the percentage of records which have positive outcome. So this is an example, again, of binary classification problem. So you need some records with positive outcome and some records with negative outcome. In this case, it's generally around 40%, which is very healthy and stable, except something really weird happened around 1st of September of 2017. There was again a business workflow or business process which went in and created a bunch of records, almost all of which had negative outcome. If I feed this into a machine learning algorithm, it would think, first of all, that feature, last modified date, has superhuman predictive powers, and it will also think that value has some great predictive power when it doesn't. So it's gonna, again, perform very bad in the production environment, talking about dirty data. And the final example is abuse of feature types. So on the left, I have a very typical text feature, which you're all familiar with. On the right, I have this feature called last open stage, which is an actual text feature in Salesforce. And if you can see, it doesn't look like a text feature. It's actually a categorical feature. To make matters worse, one of the values of that feature is actually causing hindsight bias. So the light blue bars represents the number of records which have a positive outcome when the feature has that value. And the dark blue bar, number of times it has a negative outcome when the feature has that value. So when last open stage has a value of opportunity 1, almost all of them has positive outcome. Again, it's leaking information about the label into your training data set, and hence this model, again, is going to perform really bad in the production data set. I'm hoping at this point I have convinced you, or at least tried to convince you, what dirty data is all about, what unknown data means in the field of enterprise machine learning, and what kind of problems it can create for your models. I want to pause here and emphasize a message. There are tons of machine learning libraries, frameworks, and algorithms out there in the community today. However, almost all of them, 99% of them, tries to improve the modeling stage, the machine learning algorithms. Every other day I read a paper where they try to claim that they are getting a fraction of a percentage more accuracy than the next best model. This is all great, but the problem is the bottleneck is somewhere else. It's in the data. So you can try to excessively optimize your machine learning algorithms or even invent new ones, but that's not going to solve the problem of actually deploying a real-world machine learning applications. And in the morning, we heard about democratizing AI. So that's not going to happen by just, improving machine learning algorithms. So how does Salesforce solve it? No, it's not one silver bullet which solves all the problems. It's actually a combination of statistical measures, mostly math. And we have been working on building this automated machine learning library which tries to automatically use the statistical measures to figure out if your features are really predictive or if they're too predictive and you're causing hindsight bias in your data. And so I'm going to try to give a sneak peek of some of the solutions. The first thing is very simple. You do old school statistical analysis of your features, like what is the mean, what is the standard deviation, how many nulls do you have, and the main purpose is to weed out those features which doesn't have acceptable ranges. An example is, let's say a feature is age, going back to the Titanic example. If you see that its mean is like -2, there is a problem with that feature because there is, people are not -2 aged. Similarly, if there is a feature with a lot of nulls, there is again a problem with that feature. So maybe it's a good idea to drop those features because they are creating noise. But that's only going to take you so far. The next thing we started working on is using some statistical measures to figure out the correlation or association of the feature with the label. For numerical features, we use something called Pearson correlation. There are two objectives. A, if the feature is not very correlated, almost zero correlation, again, it's causing noise. So that feature is not very important. So it's probably prudent to drop that feature. And B, if the feature is extremely highly correlated, then there's a problem. It's probably leaking information about the label into your data. So you might want to think about and drop those features as well. Pearson correlation works great when your feature is numeric, but many of the times it's not the case. We have categorical features. In machine learning world, categorical features are vectorized into numbers, and if you do so, it's become so sparse that Pearson correlation won't be able to catch the kind of association that I'm talking about. So in such examples, we use something like Kramer's V. It's similar to chi-square test, which actually can detect this kind of association of the feature with the label. Things get more complicated now. So imagine you have a numeric feature which have a very okay Pearson correlation. So it's not too high or it's not too low. But there are certain buckets of that numeric feature that is very highly correlated. So it can be like 0 and 1 values are very highly correlated or some other buckets. And the way to detect those problems is to use a decision tree to automatically bucketize your numeric feature. And once you do that, you will get a categorical feature, and then you can use something like Kramer's V again to figure out if this feature is problematic. One of the examples I mentioned earlier was about drift, that is, your feature set is inconsistent between your training and the scoring data. To solve that problem, what we started doing was doing distance matrices for the features between the training and the scoring. For example, you can use J's divergence to figure out that how different the features are distributed in your training and scoring data. If they're too much of deviation, then I think the data has drifted so much that you might either want to retrain your model or you might rethink about the features that you're using in your model. Imagine the example that I talked about of abuse of feature types. So at Salesforce, we introduced a rich hierarchy of typed features, like categorical and numeric. So here, what we would do is, if a feature is said to be text, we would do a cardinality check on the feature to really figure out if it's text or not. Maybe it's categorical disguised as a text, and vice versa. Similarly for numeric and other type of features. And lastly, most of the times in machine learning, you do feature engineering. So you might have a parent feature, you would do a derived features, then you would derive a bunch of other features. And the point of doing feature engineering is to capture signals which are not captured by the raw features. And once you do that, you can also start capturing those leakage kind of signals at the derived feature level. So what we try to do is we have a tree and we try to know the lineage. We save metadata so we can trace back all the way to the root feature if a particular feature is problematic. And thereby we can drop those features from the data set in order to clean it up. So doing some of all of these tactics, here is an example. Sorry, went too fast. Here's an example of using the automated machine learning library, which is actually automatically trying to clean up your data versus a very experienced data scientist hand tuning and handcrafting. So on the circle of the left, we have the number of features which was removed because it was problematic by automated machine learning. And on the right, we have number of features removed manually by a data scientist. Of course, the machine missed several features which a data scientist found, but it's promising to see that it was able to detect more features which was creating problem than a data scientist. Another thing that I want to mention is this is just one data set and one use case. So at Salesforce, we have hundreds and thousands of customers, many different data sets and many different use cases. So if you have to do that with a data scientist hand tuning and handcrafting, you would need an army of data scientists, and this won't scale. I also wanted to share some live prediction results using this new technique. The blue curve is using none of these techniques, using any standard machine learning library that you can find in the market. The red curve is our first version of AutoML, which has some of these techniques used. And the orange or the yellowish curve is the latest and the greatest. And on the x-axis, we have the trained data set, the holdout data set, and the live evaluation data set, the data set that's actually the machine has never seen. This is a classic definition of what hindsight bias is. Extremely high AUPR in your training and holdout data set, almost close to 1. Whereas once you do evaluation on the real world, it nosedives like 0.8. However, if you see, the orange curve is much more steady. It doesn't give that high AUPR in your research environment, but it doesn't drop too far either. So it's much more reliable than what you're seeing in your research environment in the 4 walls of your lab versus what's actually happening in the real world. And we performed the same experiment with another evaluation metric called, we did the same thing with AUROC, and again, we saw the same picture. The blue curve dropped a lot in the actual live prediction, whereas the orange curve stayed more steady. So So this is all great. You have unknown data, you're being able to figure out some of these problems. So one of the things that I do want to mention is a bigger challenge while doing many of these things is figuring out what are the right thresholds. What do I mean by that? So imagine I talked about Pearson correlation. So there is a value of the Pearson correlation. How do you know at what point it is a problematic feature, it's causing leakage, versus it's actually a true predictor, it's a good feature? Is it 0.75? Is it 0.90? Is it 0.95? And the value would change based upon your data set and your use case. And that's just one threshold or one parameter. I talked about many different statistical tests, so there is a permutation of the parameters and threshold which is perfect for your data set and for your use case. And to illustrate the complexity, I have this fancy little GIF animation. On the y-axis, we have the objective function of AUROC that we are trying to optimize. And on the x-axis, I have this thing called config. A config represents a combination or a permutation of those thresholds and parameters. And on the top right, we have the customers we have been running this experiment on. And if you see, every single time a different config wins. So there is no static threshold that you can win and you can get away with it. You have to run this on different customer data, and different use case, because based upon that, your threshold and your parameters might be completely different. So finally, the key takeaways from this talk: consumer machine learning is different from enterprise machine learning. Bias in data has created a bottleneck in enterprise machine learning, and you cannot solve it by excessively optimizing your machine learning algorithm or even creating new ones. A combination of statistical methods and feature engineering can help to detect and fix it. And finally, a very important point is determining the right threshold is key to differentiate between what is a true predictor, a feature that you would like to keep, versus something which is garbage, something you want to throw away. So finally, one of the things that many people ask me when I give this talk is, we're building this library and we are adding these capabilities as a part of this library. Is there any thoughts about open sourcing some parts or some aspects of it? So the answer is yes. We are planning to open source our machine learning library. So right now it's in a private beta. So if you want access to it, you can go to this link, and if you provide your GitHub handles, we can add you to that. So that's all I had for my talk. Thank you very much. Questions?
Hi, thank you for your talk. What about some perspectives of automating processes for unsupervised methods?
So right now we are only working with supervised machine learning. So you would be surprised how many problems can be fixed with binary classification, logistic regression problems, and multi-class classification, even linear regression. So unsupervised learning hasn't come up so much in the enterprise space as we would have thought to be. So there are too many problems with just regular supervised classification problems. But it's a great question. Thank you so much.
Anyone else?
Okay, so the overall picture is a system for detecting undesired bias.
Mm-hmm.
And how applicable is the same framework for detecting bias that is not leaking information, but bias that you would want to get rid of anyway, like unfair gender bias or something like this?
Yeah, so that's a great question. And the other kinds of biases which are there, so bias is a huge umbrella topic. And someone mentioned that you need a whole PAPIs to actually talk about all the different kinds of bias, including gender, race, fairness. There's confirmation bias, and there's other kinds of bias out there. This is particularly dealing with data-related bias, and also it's very specific to hindsight bias and label leakage. So some of these tactics won't work to get rid of like fairness or gender-related bias. But I'm sure there are other techniques that can be applied for that.
Hi, there's been a lot of talk about the interpretability of deep learning models versus domain knowledge and the role it takes on assessing the results of the models. After using extensively this AutoML, did you guys find that the results, the the dropped out features, they are interpretable some way. Can you guys eventually explain to a client or things like that how those features were dropped?
Yeah, so I think, again, that's a great question. It seems like you're working with clients because our customers constantly ask that when we show them predictions, they ask the why question because trust is a big issue. So we have certain methods in which we can actually try to interpret that. Interpretability also is very interesting because you really need to dig deeper exactly what they really mean by that. For instance, in certain fields like legal, I think there was a lot of talks around legal, they actually want to know how the machine learning model worked and got to his decision. It's also true in healthcare and insurance industry. Finance is another example of industry. However, in some of the other industries, they don't really care so much about how the model got to the solution. What they care about, they're trying to get insights. They want to make the model more actionable. So if you can provide some insights, not exactly explaining how the model works, that can actually solve many of those problems as well. But we keep a lot of information about how the features were engineered, like which features were dropped. Many of the statistical measures like correlations and Kramers can also be used to actually explain what are your top features and rank them, as well as your bottom features and rank them to actually drive trust with the system. Again, interpretability is a big topic. I actually had another talk on interpretability where I talked about and I covered some of the more details. And for deep learning, generally what they do is they use a substitute model. They would use a what you call surrogate model. So you use a deep learning model to do the actual modeling, but you use a logistic regression to explain what the model is all about. So that's what they do. Yeah.
Okay, we have time for one more question. Anyone?
Yep.
Thank you. This is just to clarify the things that you've automated. You mentioned that you would detect when you should retrain your models. Is that also something that's being automated?
Not yet, not currently. So we have a schedule, unfortunately, but with some of the things that we are putting together, it can be automated. Yeah, so, but again, a great question. It can be, but yeah, not yet. We're not that far in machine learning as most people think we are. So most companies are not that far.
Thank you.
All right. Thanks,
right.
everyone. Hope you have enjoyed.